Hi everybody, welcome to this series of lectures on applied statistics, and today we shall discuss a very important discrete probability distribution that is called the Poisson distribution. This lecture will also contrast the Poisson distribution with the binomial distribution, and if you need to refresh yourselves, the link to that video is in the description beneath. So here's the problem. Suppose on average, a call center gets 200 calls per day. We want to know what are the chances of receiving 300 calls per day. So let's decide some notation first. Let us call the arrival of a call a success. The success basically means an event we are interested in. Let's also denote the average success rate with the Greek letter lambda. So the lambda equals 200. Let's denote our desired rate of success with k to continue with the notation that we developed for the binomial distribution. So k equals 300. Let x be the random variable that represents different number of daily calls. So x can take on many values, and we want to know the probability that x will have a value k, that is 300 in this case. Note, we must assume that the average rate of success does not systematically vary. And this is a very important point, so please listen carefully. We must assume that the average rate of success does not systematically vary. For example, the call rate does not drop or rise regularly on certain days such as weekends, etc. Now we have seen that we can use the binomial distribution to model k number of successes with this formula that is on your screens. Here p equals the probability of seeing a success. But what is that probability here? Also, n is the number of trials, that is the number of times we observe whether there is a success or not. So what is n? Is it 1? After all, we are modeling k successes over a 1-day period. So let's try to apply the binomial distribution. To do that, let's find p, that is the probability of success. So perhaps p equals the number of successes over a given time period. But if we substitute lambda and n, we get 200. Clearly, a probability cannot be more than 1, so this doesn't work. How about we split a day into 24 hours and repeat the process? But still the value is greater than 1. Let's split further into minutes. Now we get p equals lambda over n, which is equals 200 over 1440 minutes, and that equals 0.14, which is less than 1. The binomial distribution also requires the probability of failure q, which is simply 1 minus p, and so that is 0.86. So looks like we are all set to apply the binomial probability mass function as shown here on your slides. So you can pause here and work yourselves through it if you're interested. Okay, so before proceeding, consider this. It is possible for multiple calls to occur almost at the same time. Now that is not allowed in a binomial distribution. Notice n in a binomial distribution represents the number of independent Bernoulli trials. And each Bernoulli trial, by definition, can have at most one success or a failure. Like tossing a coin can generate only one head or a tail, not many heads or many tails. But here, multiple calls or successes can occur at the same time. This means that if we use the binomial distribution to model the probability of the number of calls, it may work, but it will have some error. So let us try to minimize this error. Let us try to shorten the intervals so the chances of co-occurrences diminish. For example, let's measure time in seconds. Clearly, the chances of co-occurrence decrease but do not vanish altogether. After all, it is still possible for two calls to be made at the same time. Note, as the intervals shorten, the number of trials, that is n, increases. So ideally, to exclude any chances of co-occurrence, we must make n so large that it approaches infinity. And when that happens, then the probability of success p, that is lambda over n, approaches 0. Excuse me, which makes sense because probability of success over a very small time interval must be very low. But we cannot compute the binomial distribution if we substitute p equals 0 and n equals infinity. Because then in this case, every probability equals 0, because you see there's a multiplication with 0 to the power of k. That makes sense. After all, over infinite trials, every number of success is possible, and therefore the probability of each individual k must diminish to 0. Yeah, but what do we do now? I think we need some mathematical trick to get out of this jail. It turns out that when n tends to infinity, the binomial distribution can be approximated by what is called a Poisson distribution. So here's the formula for the binomial distribution again, where p equals lambda over n. And when n tends to infinity, the formula for the binomial probability mass function turns into this expression on your screens. Hence we get what we call the Poisson distribution, where lambda is the parameter of the distribution and k is the number of successes that we want to observe. Notice when lambda, that is the average rate of success, is not directly given, it can be obtained by multiplying the probability of success p with n, where n is finite. Alternatively, sometimes lambda is given directly. For example, in the present case, lambda is given as 200 calls per day. So let's return to our problem where lambda equals 200 and we want to know the probability of observing 300 calls in a day. We also assume that lambda does not vary systematically. So let us substitute the values as on your screen into the probability mass function for the Poisson distribution, and the answer is approximately 9.1 times 10 to the power of minus 12, which is negligibly small, almost 0. Now what if we had used binomial distribution as we had set up to do when we started counting time intervals in minutes? Remember we said that that does leave some chances for co-occurrence of calls. After all, many calls can come within the same minute. Well, if we compute the probability value here, it is 1.6 times 10 to the power of minus 13. With the Poisson distribution, the answer was about 9.21 times 10 to the power of minus 12. So here, there is a tiny difference of the order of 10 to the power of minus 12. So if this difference is acceptable to us, we can recall that we said that Poisson distribution approximates the binomial distribution when n tends to infinity. So it turns out that with the given probability p, n turned out to be large enough in this example, and hence the difference is tiny between the two distributions. In general, remember the rule is that if n is large and p is small, then the Poisson distribution approximates the binomial distribution. And the reason is that with small p, the chances of successes are already small, and naturally, a co-occurrence is very unlikely. Now let us see the effect of changing n and p on the approximation error. That is, how the difference between binomial and Poisson distribution changes if we use them to calculate the probabilities. So we assume k equals 3 and we start with a low value of n, that is 9, and instead and we set p very high at 0.99. So at the start we expect discrepancy between the probability values generated by the two distributions, and so the difference must be significant. So here are the results of the first experiment, as you can already see on your screens. Here we keep p constant at 0.99. So notice as we go down, as the arrow goes down, the p, or as we mark it by ps, doesn't change. It stays at 0.99. As expected at the start, the difference is about 1.5%, or as it is given as minus 0.015. But as we go down along the arrow, the n increases and the difference starts to diminish. So that is what we expected. Now, next, we keep n constant and decrease the p. Again, the difference diminishes as we decrease p. So as we go along the arrow downwards. You can pause the video if you want and stare at your screens to verify what I just said. Finally, as we increase n and decrease p, the difference diminishes as we had expected. Now, if you want to run these experiments yourself, the code for this experiment is in the description beneath this video. Now consider another example. In this case, lambda, that is the average rate of success, is not given directly, but the probability of success is given, that is 0.02. Now we want to find the probability of k equals 3 rainfalls in any given day. Since p equals 0.02 per day, that means on average it rains 0.02 times over n equals 1 days. Now we can calculate lambda, and that is n times p, which equals 1 times 0.02, which remains at 0.02. So now that we have both lambda and k, we can substitute it in the Poisson distribution formula. Hence, the chances that it will rain thrice in the same day are very small. And that's acceptable because the chances of rain in any given day already is very low. It's only 2%. So, what could be the chances that it will rain thrice in the same day? So, makes sense. Now, much like the other distribution, the Poisson distribution also changes if we change its parameter. And that parameter is the average rate of success, or lambda. Now, if you look at the formula on the screen on top, some of you may say that k also appears in the formula, so k must also be a parameter. But no, k is not the parameter. K instead simply represents different number of successes. Essentially, k represents different values of a random variable that is Poisson distributed. So here are 3 different distributions. As you can see that as lambda increases, the likelihood of higher values of k increases. Does that surprise you? Pause and reflect if you want to. It shouldn't really surprise you, because if the average rate of success is high, then the chances of observing a high number of successes naturally increases. Now let us examine the mode of the Poisson distribution, that is the most frequent or likely value of k. When lambda equals 1, we observe that the mode has 2 values, 1 and 0. When lambda equals 2, the mode has again 2 values, 2 and 1. When lambda equals 5, the mode has again, it has 2 values, which is 5 and 4. So a natural pattern is emerging. Can you guess it? Well, I hope you have, and we can say generally the mode has 2 values, and those values are lambda and lambda minus 1. Note the code for plotting these graphs is in the description beneath this video. Now sometimes we do not have lambda or p. Instead, we are given some raw data and we are tasked to fit a distribution on it. For example, suppose we note the frequency of phone calls received over the last 150 days. As we can see, there were 51 days when no calls were received, 54 days when only one call was received, and so on. If we plot it, it does look like a Poisson distribution. Now, if you want to compare it with the plots that you've seen in the previous slides, you can just skip back and forth and see that, it does look like a Poisson distribution. So, it looks like the data is Poisson distributed. If we try to fit a distribution on top of this data, it kind of makes sense. So let us find that distribution that describes or fits this data. Okay, notice we just have a bunch of numbers, so we have not come up with the distribution formula that represents this data. And that by finding that formula, I mean fitting a distribution on this data. So to describe a Poisson distribution or to fit a Poisson distribution on this data, what is that we need to do? We have to estimate lambda, that is the average number of calls per day. So to compute the average calls per day, we simply compute the average so that each number of calls is multiplied by its frequency and is divided by the total number of days, and that total number of days is 150. And thus we receive 1.04 calls per day on average. Now, if this is a good estimate of lambda, we can compute the probabilities of observing each k using this lambda and match it with the observed data in your table. So essentially, we are going to compute different probabilities using the Poisson distribution with lambda set to 1.04. So this formula is now showing on your screens, and we have to find the probabilities for x getting the values of different values of k, where k begins at 0, 1, and so on. Okay, so let us begin with k equals 0, and if we substitute the values, the answer is 0.35, which is approximately the same as 51 divided by 150. This matches the observed data, as we can see from the table above. Likewise, we repeat the process with k equals 1, and again we find out that the probability estimate is reasonable because it matches the corresponding entry in the table. I'll leave it up to you to try and find the rest of the probabilities for other values of k and verify it for yourself that the probability estimates using the Poisson distribution are pretty good actually. But you may say, we fitted a Poisson distribution only to produce probabilities that match frequencies of the data we already know. So what's the point? Good question, if it appears in your minds. Well, the point is that once we have the probability distribution formula, just like we had in the last slide when we substituted the value of lambda, we can predict probabilities for other values of k that are not yet seen. For example, we can predict what the probability of x equals 5. Notice k equals 5, that is number of calls being equal to 5. It does not appear on the table on your screens. But because we have the formula, we can predict. So we use the same distribution, substitute lambda equals 1.04 as before, but we now set k equals 5. And the probability value is quite low. Now that is expected because we could see from the data that higher values of k are highly unlikely. So that is a very useful thing, that based on past data, we can predict future data. However, note that predicting future has its own risks. For example, suppose you collect more data over another 50 days and find that suddenly you are regularly getting 5 calls each day. So the chances of receiving k equals 5 are now 0.25 or 25%. Now this is a huge departure from what we had predicted earlier on the last slide. That was only 3.5%. Now if you plot this data, you will notice that the data does not follow the Poisson distribution at all. And that is because of this rise towards the end. Now, if that's the case, we cannot really fit a Poisson distribution anymore because the data doesn't follow a Poisson distribution. So either the Poisson distribution does not apply, or alternatively, we should calculate a lot more data over a much longer period of time and update all our estimates. All our estimates, by that, I don't just simply mean the estimate for k equals 5, but all the way from k equals 0 to whatever number of k values of k that we were observing. They all need to be updated. And this is because maybe you have suddenly become popular and those silent days are now a thing of past. So your old data has gone stale because there has been a systematic change in the situation. So remember, when you are in the business of predictions, keep collecting new data because you never know when your past patterns change. Finally, we shall wrap up this lecture by mentioning a property of the Poisson distributed random variables, and that property is that if you have two such random variables, that is two Poisson distributed random variables, then their sum is also a Poisson variable. Suppose x and y are Poisson variables with lambda values as lambda 1 and lambda 2. Then x plus y is a new Poisson variable and its rate of success equals the sum of lambda 1 and lambda 2. For example, if x and y are Poisson distributed incidences of rain in two cities, then x plus y is their sum. Note, however, rain may not have the same daily chance throughout the year due to seasonal variations. So to predict the daily trends, Poisson distribution should not be applied over the whole year. Instead, you must model multiple Poisson distributions, one each for a different season, by considering the different chances of rain in different seasons. Anyhow, with that, we conclude this lecture, and we'll see you in the next one. Goodbye.